Okay, so now we're going to start the point groups. We're going to do, for today, we're going to do point group 1, 2, and 3. That's P1, P2, and PM, and then that'll take us up to Wednesday for our quiz. I'm going to show you exactly what the quiz is on. So if we start out with group P1, we take the horse, which has a point group 1, and we add it and we translate it, and here we get our crystal of horses, if you will. Here's a molecule. This molecule doesn't have any symmetry. It has point group 1, and likewise in real life, this is the way this molecule looks when you translate it. Now we have ways of describing well, first of all, we have translation along T. The translation generators are represented by T10. That means you translate along A1. So here's the direction. A would be downward. So that would be T10 would be represented by a translation A coming down like that. T01 would be nothing in A and 1 in B. So here we go along the Y. Remember, this is the Y-axis, this is the X-axis. Since the displacement vector is equal, we can write that in general of UV equals UA plus VB, then the displacement vectors are just what I described them to be. Now let's look at, and here's our generators. Keep getting ahead of myself. Now let's look at the two descriptions of the space group. We have two diagrams which describe it. Remember, for the point group, we have the stereographic projections. Here we have the general position diagram and the symbol diagram. And the general position diagram here, we have Y in this direction and X coming down, and we have the point put in the positive quadrant, which is right here. Only now we have translation. So to indicate the translation, we translate down to one along X. So we get right here with the red circle. We get the blue circle. We'll be translating one along Y. And the purple circle gives us one along X and one along Y. The point here is that we have lattice points here. Each lattice point is identical. So when you're doing these diagrams, the general position diagrams, you have to look at one check to know that you're right, is to look at each of the four corners, because they're set up, that's the way they're set up in the lattice. Now the symbol diagram, remember the symbol for the point group 1 is nothing, is just itself, so that's all it is. Now we're going to move on to point group 2, which is P2. So we have, in this case, our object consists of these two horses related by a twofold. So here you have, so if you want to, you could consider that I have the twofold, the operation twofold, relating the top horse to the bottom horse. Now the advantage of that is, suppose you had to calculate this area, and there was a complicated molecule, and there were 100,000 points that you had to calculate. If you have to calculate, if you can make use of the twofold, then you can calculate this part of the horse, this horse, and then operate the twofold on it. So all you have to do is operate 50,000 points, and you operate the twofold, and that gives you the other 50,000 to give you the total projection. And we call the minimum amount that you need to calculate, we call the asymmetric unit. So the asymmetric unit is the smallest part of the unit cell that, when operated by the symmetry operations, produces a whole unit cell. In this case, we only have one symmetry operation, the twofold, so we will produce that. The asymmetric unit is not unique. You could have used the bottom half. There are other ones that you could use as well. And the international tables for crystallography will give you, this one is, will say P2 is X between 0 and 1/2. So here's X, and we're going to 1/2, and Y is between 0 and 1. So the international tables will give you an asymmetric unit. They'll tell you how much you need to calculate. So here's our space group P2, and we've put all our horses. Our crystal consists of the unit cell. Each unit cell has these 2 horses in it, and the 2 horses are related by a mirror plane. Now, what's the most fascinating thing about P2, I think, is if you look carefully here, do you see any other two-folds? The two-folds would be a result of the fact that we have a periodic array. Now, turn this off and look. Okay, I guess you found maybe one. Here's one here, which relates this horse to this horse. You can see the tail goes into the tail, the head into the tail. In fact, this one will go into this one down here, and this one will go into this one up here. This twofold is universal, as this one is also universal. And you can see each lattice, each of the unit cells are related along the line, related along by this green twofold. Now, are there any others? Well, let's look, and there's the yellow ones. Do you see going from here to here? We're having this foot going to this foot, etc. And finally, there's one more, and that's this head to this head, that tail to that tail. And so we put in one twofold, we apply the translation in 2 dimensions, this periodicity, and we end up with 3 more. These are exactly equal, but they're distinct, because if you look at the neighborhood of, say, the red twofold, that neighborhood is very distinct. It's got all these feet here. And if you look at the green one, you have 2 heads in that neighborhood. So that they're not on the same lattice. All the reds are actually one lattice. Now, if we want to abstract the information that we've looked at so far, we could just take one unit cell. And furthermore, it doesn't matter what the pattern is. You could put any pattern here as long as the 2 are related by a twofold. So let's remove that as well. So here's the symbol diagram as an abstraction of the diagram that we've had from the pattern. So we can go from the pattern to the symbol, you go from the symbol to the general position, and vice versa. Okay, so now let's look at the primitive, the asymmetric unit. We've now put it in pink, and we have the general position diagram, which I'll explain in detail in 1 minute in the next slide. And here's our general position diagram. So here we have now I'm going to describe the general position diagram in detail. The first thing you do is you put in the identity, then you translate the identity. Always do that in that order and you'll get it right. Then we have a twofold, and we're going to put a twofold right here, and that's going to generate the red point here. It's going to go from green to red by the twofold. Now these are all lattice points. They have to be equal, so we need to have a red for each position here. And also we need to have another way of looking at it is we could translate. Remember, we can always translate by one cell, so we could translate this over here, or we could translate it along X, or we could translate it along XY. Now in the unit cell itself, notice we have two points in our general position. And here's our symbol diagram. Well, on the corners we had our twofold, and then let's see where else we have the twofold. Yes, the green is going to go right halfway in between here, so we have become colorblind. Now these are all equal, so this green is related by a twofold to this red to this green by this green twofold, and likewise down here. We can find our others. If you look here on the general position diagram, you'll have this related to this related to this by the yellow, and likewise on this side. And finally we have the symbol in the center, which would be right here, and that would relate this to this to this one to this one, and that one to that one. and the position is a set of symmetry equivalent points. In P2, the green and red circles taken together represent the set of symmetry equivalent points that form the general position. Notice that in the unit cell there are 2 points. So here's our unit cell from corner to corner to corner to corner, and here are our 2 interior symmetry points. And here's our P2, our asymmetric unit. The asymmetric unit is shown in pink. Here's our generators, and the lower half is generated by the red rotation. And notice that the area of the asymmetric unit is 1/2 the area of the unit cell. Now, remember I had you get the book, and so you can open up to the page that gives you the P2. You can find it, and you'll see that on the left you always get the International Tables. Gives you a huge amount of information. You get the crystal system, the point group, the space group, and the space group number. They're numbered. In 2 dimensions we only have 17, so we don't have to worry about it too much, but we have 230 in 3 dimensions, so it's nice to have those numbers to keep track of them. And you have 3 dimensions, those numbers that you have in for your personal space group, like 18 is one of these numbers. We have the general position diagram. Notice that's no colors, even though those circles we don't, well, in this case we don't have, the colors are the same, but it's in the symbol diagram that really matters. Notice that there's no colors. The International Tables is published in black and white, so that the crystallographers are essentially colorblind, and we know that these say 4 on the corners will form the lattice, and we know that the rest are generated. Or we could take this one and generate the other 3. But it's for when you're beginning, I think it's nice to see those different colors and see how they separate out, because it tells you a lot about what's going on. And then the International Tables will also give you the asymmetric unit. Now, you're going to get your quiz this week is going to consist of 2 parts. The first part is going to look exactly like this. I'm going to give you a projection of a molecule, of a crystal that consists of molecules, and then I'm going to give you these symbols. So I'm going to go through that with this example. So I expect you to really know this example. So find a 2-fold. Now you have to look through this whole diagram, and I think the easiest 2-fold that I found is this one right here, because you can see this little molecule that's got a 2-fold in it, and you can see this array of a blue and some greens there, that goes into that. You can see immediately around this you have the red going to the red, you have the white going to the white, you have this fused double ring here going to this fused double ring. So I think you can see that we can put a 2-fold there. The 2-fold is universal. It will take, for example, this little moiety here, and it will come down and it will go to this moiety down over there. So now, once we have one 2-fold, we have to look for identical ones. So you come along here, and then this is the next one that I saw, and then and then I want to come down and get the second dimension. So I come down along here and I look for this little two guy. So there he is, and we have another one over here. You want to mark all the 2-folds, so you can see you get an array of 2-folds here. The example that I'm giving you is going to be a little easier to see than this one, but I want you to study this one carefully. Now we can connect 4 of them and get a primitive unit cell. And I want you to notice that the this side is equal to this side. You can see how this little formation is right here to the left, and here you can see how this line goes right through these 2, for example, and you can see how this moiety is like this. It's a little bit off here. This one should be entirely outside. sometimes it's a little hard to draw these. These are drawn by the molecules are computer generated in a program which I wrote, and I superimpose these unit cell. Now you want to also now begin to look at the rest of the symbols. So now if you look halfway between here and here, you'll see, let me take them out so that you could look at that. You can see that there's a twofold here. You can see this group goes into this group. You can see this group here goes into this group here. These two yellows go into these two yellows. So you're always going to look for one halfway between, and of course it's going to be on both edges. And we can look on the other edge, and we can see this moiety goes into that moiety. We can see this moiety goes into this moiety. And so we see another twofold there. Look at these diagrams very carefully. And then finally we have one in the middle, a purple one. So we have three of them, a purple, a red, and a green that were generated, and the yellow was put in. Like we could have put in any one of them and generated the rest of them through with the translation. The purple one will take this group here into this group here. You can see this moiety goes into that moiety. So carefully study it to convince yourself that you've gotten it. So now we've gone this far, and now we've put in the asymmetric unit, and here's our asymmetric unit. So that's what you're going to have as the first part of the quiz. Now let's go to group PM, which is number 3. Here's two molecules here, and you can see very clearly that they are related, the top one to the bottom one. There's a mirror plane right in there. So you look carefully, you can see the red to the red, the yellow to the yellow, the blue to the blue, and you can see how this one is slanted up and this one's slanted down like a mirror. Now we can put that, the mirror is called MY because it's along the Y, and here's our asymmetric unit. We can put all of this into our lattice, and when we do that, here's our mirror plane that we put in. Have we got anything generated? Well, always look halfway between the two symbols, and you see another mirror plane right here. Do you see that? And we're going to mark that green. That's our generated mirror plane. And now I'm going to give you the general position and symbol diagram for that previous pattern. So you always start with the identity, and now we have a mirror plane along here. So we indicate the change of handedness by a comma inside the circle, and so here is our identity goes into that, and now we can add 1 to it in each of the directions so that our excuse me, the lattice points are identical, and here's the other two. And now we can put in our asymmetric unit, and notice that there are 2 points in the asymmetric unit. You have one up here and you have one down here. For our symbol diagram, we're going to put in the mirror planes that we put in originally, and they're related by a translation. And we look and we see here, and we can see this goes to this and this goes to this. So we have a mirror plane halfway between along where the red line is, and here is the asymmetric unit. Now finally, your second part of your quiz on Wednesday is going to be a problem very similar to this. I'm going to give you a pattern, and then you're going to have to tell me the general position diagram and the symmetry diagram of that pattern. So the very first thing you do is you put in the identity. The second thing you do is you look at the pattern, and I think you can see a mirror. Can you see the mirrors down here? There's a mirror there, a mirror there, a mirror there. So we're going to put in one mirror. Let's say it's there. And then if we have a mirror on one side of the unit cell, by translation, of course, we'll get the mirror on the other side. And now we will put in the mirror tells us where to put in the next point. And notice this has this comma in it to show that we've had a change of handedness, and so the mirror takes the point from across the mirror. So you have to look where the mirror is. On the previous one, it went the other direction. We had the mirror going in the horizontal direction. Here we have it in the vertical direction. And we can now put in the rest of our points because these are all lattice points. Okay, and then we look at this and we say, okay, let's look about halfway between here. Or we can say, let's look at this point here. Is a mirror going to over there? Now what about if I want to go from here to here? Well, there's a mirror right in between. Here's a mirror right in between there. So I have a mirror going down like this. So I have the symbol diagram. We have to look at what direction. We have to look carefully at the pattern and match the pattern according to the symmetries. And then we have our asymmetric unit. Notice the asymmetric unit will be bordered by the mirrors, and we have one point in each of the asymmetric units. And if we had drawn it across this way, which of course we don't, you wouldn't do that, you would have 2 points and you would have no way of generating. Now let's look at the pattern. Okay, now the pattern, here's, if I put in my mirrors, notice that this red mirror is identical because of the way the tails are. See how those tails are identical? This little part is there and there. I could have put another red one, would go here. And now the generated mirror plane is right in the middle here. And if I want to have a unit cell, I could bracket off those 2 dogs. They're related by the mirror plane. And you can see the asymmetric unit would be this dog because you need his tail and his head and everything, and then you put that into the mirror plane. If you would put the mirror plane along this way, you would have double set of heads and no tails at all. So you have to consider how the pattern is carried over. That's all for now.